Hello guys, this is an interesting work on neural architecture search and I'm really excited to share this work with you. The link to this paper is provided in the description below. The name of this paper is Weight Agnostic Neural Networks by Adam Gary and David Ha. So the way I will be presenting this work will be through the neural architecture search field because I believe this is the most natural way to approach this paper. So what exactly is neural architecture search, also known as NAS? This basically involves algorithms that automatically design the architecture of the neural network for a given task. The most important part of any architecture search method is the search strategy that we use to navigate the architecture search space. The two most popular methods are the evolutionary algorithm and the reinforcement learning. In this work, we will be focusing on the evolutionary algorithm part. Now, for any search strategy, you will need a way to evaluate a particular architecture, such as the architecture 1. What you can do is that you train the architecture 1 on the given task and then use the trained architecture weight to evaluate its performance. You will have to do the same thing for another architecture as well, and so on. This is normally the bottleneck part of the neural architecture search methods. So now what this paper called Weight Agnostic Neural Networks is proposing is that they perform the architecture search without explicitly training each architecture separately on the task. Instead, they initiate all the connections in the architecture with a single shared weight parameter sampled from a uniform random distribution and measure the expected performance. What they're hoping to achieve is that the neural architecture alone encodes the solution to a given task. The paper does provide some interesting findings. This idea is based on the observation found in nature, where we see that shortly after hatching, ducks are able to swim and eat on their own. So, how does this method work? This is a general overview of the whole process. In the first step, an initial population of minimal neural network topologies is created. Then comes the evaluation part, where you have to evaluate each architecture in the population. So, for evaluating each architecture, you would initiate all the connections in the architecture with a single shared weight parameter out of the list of the weights provided for a single rollout. You would do it for all the weights in the list. This is done to reduce the variance during the evaluation. At the end, the cumulative reward is recorded. The third part is the ranking, which is done based on the performance and the complexity of the neural network. The highest ranking networks are chosen probabilistically, wherein 80% of the cases networks are ranked according to the mean performance and the number of connections. This makes sure that the given two different networks with similar performance, then the simpler network is preferred. And the other 20% ranking is done by the mean performance and the max performance during the multiple rollout. Now the question might arise, why do it probabilistically? Well, the goal of this method is to encourage minimal and modular networks. But to gain performance, you will need to increase the complexity of the network. This complexity is captured by the number of connections as shown in the 80% case. But this constraint becomes very difficult to achieve because sometimes you have to do multiple structural changes in the long run to gain any sort of performance gain. So this probabilistic ranking is done by relaxing this constraint. This can be thought of as a exploration and exploitation part of the method. Based on the ranking, which is basically network selection, now you would perform the mutation to create the next generation population. There are basically three mutation operators used in this paper. Let's say you want to mutate this network. Now the first mutation operator is insert a node, which is done by splitting an existing connection into two connections that pass through the new hidden node, and the activation function for this new node is randomly assigned. Next is the add connection operator, where new connections are added between previously unconnected nodes. And last is the change activation operator, where the activation functions of the hidden nodes are changed and they are assigned at random. Following are the activation functions that are considered. Lastly, you would repeat the process of evaluating the new population and then creating a new one, and so on. Now for the results, the method is tested in 3 different tasks. The first task is the cart pole swing up, which is a classic control problem where given a cart pole system, a pole must be swung from the resting to the upright position and then balanced without the cart going beyond the bounds of the track. The second is a bipedal walker, which involves guiding a two-legged agent across the randomly generated terrain, and the rewards are awarded for the distance traveled. And lastly, the car racing task, where a car is controlled and is tasked to visit as many tiles as possible of a randomly generated track within a time limit. Now the results are presented with 4 different categories of weights for all 3 tasks. In the first type, individual weights are drawn randomly from the list of weights uniformly. Here a single shared weight is drawn from the list of weights. In this category, it involves the highest performing shared weight value in the list of weights. Here the individual weights are tuned using the population-based reinforced algorithm. Now, if we look at the results for the cart pole swing up task, we find that the conventional fixed topology networks, which are used as a baseline, only produce useful behavior after extensive tuning. In contrast, the weight agnostic neural network method performs well even with random shared weights, but they do fail when the individual weight values are assigned randomly. We see similar results for the bipedal walker task. Lastly, we also see the similar result for the car racing task as well. Now here we see the weight agnostic neural network topologies as developed over time for the cart pole swing up task. Early network at generation 8 performs poorly with nearly all weights, as can be seen in the reward graph at the bottom. In generation 32, the neural network becomes more complex, learning relationship between different input signals while improving the performance. While in generation 128, the complexity is added to refine the balancing behavior of the elevated pole. Lastly, the method was also applied for the image classification task with MNIST dataset. Restricted to a single weight value, the proposed method is able to classify MNIST digits as well as a single layered neural network with thousands of weights trained by gradient descent, though it cannot beat a two-layered CNN network. In conclusion, I would like to say that the proposed paper is quite interesting and I would like to see if it can be extended further. Since the present idea was tested for a low-dimensional input space, I wonder if the idea can be combined with the idea of SuperNet that has shown good results for the high-dimensional image space. Thank you for watching this video and always remember to keep trying.